So, once the top layer is ignited, the sintering begins. The progress of sintering process after the ignition of the top layer of sinter bed is shown below schematically. So, there is a so when the process, I think probably it can be understood much better way from this figure how these zones. So, in the starting you have a green pellet. Once this under the ignition hood this sintering start from the top, it comes out that. So, this is already now top one is a sintered one, but because the wind works are located at the bottom. So, it is sucking the air, the fresh air atmospheric one from the top. So, due to the forced convection, we will talk a little bit about the heat transfer later. So, the top sintered layer get cooled because at 25 degree or 30 degree Celsius air is entering from the top, and so which cooled it down the top layer, and the sinter and suppose the sinter which has made or we, this is actually showing somewhere here the intermediate region. So, like this layer is already sintered and became cold, and this is getting sintered. So, this is the this is also already hot and getting sintered, and the combustion front has already moved forward after sintering this. So, this is a hot sinter and the hot air now is coming there because this is a hot already sinter and assisting supplying the oxygen to this front. The preheated hot airs are coming in this one, and this is a combustion zone. Now, from the combustion zone whatever air is coming out, they are quite hot and they are under suction. So, what and below the combustion zone all the pellets, they are green pellets. So, what it does, it preheat the green pellet in this combustion zone. So, mostly calcination and those thing occurs in this. These are already actually preheated because the temperature is very high. So, calcination and other thing is occurring in this zone, and when it passes from this pellet gets colder and colder. So, temperature keeps on dropping. You can see the temperature this is the cold one. So, temperature actually it should start from here. So, 25 degree it keeps on increasing because this flame front has traveled to here, and when it reaches to the combustion zone, that is the maximum temperature which you are having around 1300 degrees Celsius. And then these gases start cooling down because you have the cold pellet. So, these gets heated up, and because the temperature is still very high in this region about 1100 or so. So, decomposition of carbonate occurs in this region, and below that temperature then because this is all endothermic reaction. So, temperature further drops, and as the temperature is dropping, then when the temperature is around 600 or like that, you have a drying zone. So, like pellet gets dry or any other chemically bonded water and other thing comes out from this, and in fact, whatever moisture is there, that also comes out in this region during drying zone. So, and temperature continuously decrease. So, what has happened because this zone is still quite hot about 400-500 degrees Celsius, the moisture evaporation takes place. But once this moisture evaporation moisture now is coming with the gases over here. So, it and at the next layer is a cold one. So, recondensation of the moisture occurs here. So, at one place the evaporation is occurring above this, but here recondensation of the moisture is occurring, and so pellet get quite wet actually at the bottom, and even water can come out from the bottom in condensation, and temperature drops even quite low in this region at the bottom, and this is the way, and because this is moving, so the top one keep on getting sintered, and the flame is traveling downwards. So, the next layer keep on getting sintered, and that get sintered, then it travels further down. So, plastic sinters you have, and then you have a dry zone as we discussed, and by the time it comes out it all gets sintered. So, this is showing more about that how the sinter bed look like. And if we talk a little bit about the heat transfer here, so that is the thing which we discussed. The condensation is occurring after that in this zone, because the moisture which has evaporated recondensing in the lower temperature zone. You have a sintering zone about 1200 degree C, then you have a heat front cooling zone, and the top one really from the atmospheric air get cooled down below this 40 degree. And so, mostly you are having a forced convection here, conduction and radiation plays a small role in this region, but not that one. It is mostly the forced convection. If you are aware about the heat transfer, then about this I am talking. If not, not to worry too much about it. So, the main now one important thing if to look at this, we are having at the flame front. If flame front is going to continue like this, then it is going to really, and that temperature 1400 degrees Celsius, and that is going to damage the strand and the heart. And so, the main thing in the sintering, to operate the sintering machine in a proper way and a good quality sinter, it is important that burn through point of the sinter making should end as close as possible. So, sinter making should end as close as possible of the last wind box. So, this is shown here. So, this is a sinter bed already sintered, and you are saying this is a sort of a flame front. So, it should finish, the full sintering should finish almost at the end of the last wind box, and where the discharging occurs. So, there is no damage to the sinter strand, and immediately once this finishes, it falls down and sinter breaker is there. So, top material is usually cool, but this material is a very high temperature one, but it is better to have that high temperature sintered one, and it breaks down by the sinter breaker. So, this is a very important thing for the sintering process. So, whatever people do, they always talk about the burn through point. So, this is quite important. So, once this sintering is over, then it comes about the cooling and screening of the sinter. So, which you have seen those sinter screen one there in the figure. So, at the end of the burn through point, end of the grate, a rotating hammer breaks down the discharged sinter into smaller sizes, and which are screened and cooled. So, plus 15 millimeter goes to the blast furnace, and this goes as a hearth layer, and below the 10 millimeter goes to the as a sinter return again to make the green pellets. So, some correlation has been proposed for the sinter productivity in this form. So, where P is the productivity of the sinter machine, B is the bed depth excluding the hearth layer. So, it is about the green pellet depth, and H is the width of strand, and B is the speed of strand, and that is in meter per minute. This is a bulk density of the mixture green pellets, and RF is the amount of return fines generated, and which has been put into this. So, in ton per hour, and Y is the yield of the sinter from the raw mix. Based on that, one can calculate the productivity of the sinter. And typical mass and heat balance on that sintering process is given in this one. So, the mass variance about 40 to 45% ore goes in, 2 to 3% fine dust, about 5% coke, and about 5-6% water actually it goes. And the return sinter return, the return fines which also comes, it is about 20 to 22%. So, it is quite a high amount of sinter returns actually you put it into that. And then you have also the machine return, they were very fine which is coming underneath of that machine, that also constitute about 12 to 15% machine return. So, these are the input, and the output of course the return sinter, blast furnace sinter about 35 to 40% you get it, and loss of volatile 13 to 18%, and about 15% machine returns as output of the process, which gives the total mass balance of the sintering process. And for the heat balance we have this. So, in the heat balance 80 to 85% heat comes from the coke, and the flue dust constitute that about 7%, combustion of sulfur about 0.5, ignition of the gases also through the burner is about 6%, and the formation of Fe3O4. So, from hematite to magnetite it is a exothermic process essentially. So, about 1% comes from that, and total heat loss. So, heat loss to the environment, machines and various other places is about 7 to 9%. Waste gases take away most of this heat of the order of 25%. Sensible heat in the sinter is about 25%, like dehydration and calcination constitute again quite a big amount, 20 to 23%. So, you can imagine how much heat is going into this one, and you are saving coke, that much coke in the blast furnace to get rid of this action. So, always it is good to put flux with the sinter. Moisture removal around 15%, and other miscellaneous which goes as the heat loss. So, this shows the overall heat balance of the sintering process. Now, we will talk a bit about the constituent role of constituents in sintering. So, as you know, we have moisture during the granulation process. So, moisture content should be optimum during sintering process, usually 6 to 8%. Usually in sintering process it is about 6%, but in pelletization it is a little higher, it goes around 8% or so. So, it is a good amount. So, lower or higher than this moisture content adversely affect the sintering operation. So, moisture content can affect the dust generation if it is low. So, quite a lot dust will generate, and then it will affect the bed permeability, and very high also it does. So, if you look at this figure, as the moisture content is increasing, you can see the crushing strength of the green pellets, it increases up to a certain moisture content. So, 9 or below 9%, but after that it start decreasing, and fine size have higher strength than the coarser size pellet. So, but this is true in terms of when we are doing pelletization, but similar argument is held for the sintering also. So, because crushing strength is very important, when you are putting on the center strand the bed of the pellet, the suction is very high, and under that suction it must withstand that pressure drop. So, they should not lose their shape, otherwise it will affect the permeability, and higher suction pressures you need and this probably will lead to many other problems. So, crushing strength, that is where this factor comes into picture. Same thing about the drop strength, which is the moisture content, but you can't have a very high moisture just to that. You need a reasonable drop strength. So, you can choose from that. So, 8% for the pellet is a good one. For coke bridge, so this should have a correct size distribution, otherwise uneven localized heating may occur, because these all are fines, and when you are looking at these particles, 2 millimeter and 3 millimeter particle. So, the way heat would be released, it is sort of a localized within the pellet. So, 2 millimeter will give a different amount of heat and 3 millimeter will give a different amount of heat. So, that will give a different temperature gradient, and that will affect the structure of the sinter and the phase formation. So, which is not good. That is why the correct side distribution is very necessary for the coke bridge. The more coke bridge will contribute in more formation of phthalate. Now, as we know, the coke is associated with S, and S has silica in it, and which form that ions phthalate ion silicate this, and formation of phthalate actually reduces the reducibility of the sinter, which really we do not want in the blast furnace. However, it increases the strength of it, but the reducibility is much more important. So, more coke will facilitate formation of more, also the more coke facilitate formation of more magnetite and wüstite phases, thus decreasing the degree of oxidation, which is also not good. The figure, this figure shows qualitatively how the coke percentage of coke rate is affecting the various property. So, as you increase the coke percentage, you can see the reducibility is decreasing, which is due to the formation of phthalate phase, and degree of oxidation also decreases, formation of magnetite and wüstite phase, and sinter strength though increases, but because these two are reducing, so these are not good for the blast furnace as a feed when we go there, and we had discussed few of them during blast furnace description, but we will come again on this. So, proper percentage of the coke is also quite important in this sinter. Limestone is very important, as we said it is better to use limestone during sintering than in the blast furnace. So, you can save the coke. So, limestone or dolomite is added to increase the basicity. Usually basicity, if you do not have a dolomite or other magnesium based flux, then you give the basicity based on the ratio of CaO and SiO2. But if you have a magnesium based flux also, then because magnesium is also a basic in character like calcium. So, these are combined and then you put the ratio in the combined form, CaO plus MgO divided by SiO2. So, this increase the basicity of the sinter when you are putting any flux. So, naturally this content is increasing, so you will increase the basicity. So, depending on this ratio, sinter has been classified under acidic or basic. So, acidic sinter when no limestone is added. So, naturally the ratio would be 0 of this when no limestone is there, and major phase in that case is phthalate. So, you will get a stronger sinter, but poor reducibility. So, in some cases it may require, but mostly it is avoided. So, the basic practice nowadays is about the basic sinter. So, basic sinter, these flux sinter are further classified into again various basicity based on their basicity ratio. So, self-fluxed sinter, where the ratio of the basis this basic and acidic compound is about 1, we say basicity 1. So, and in terms of CaSiO2, if it is about 0.8, so this actually you call the self-fluxed sinter, and that increase slag volume in this case is increased in the blast furnace, because you have to really add extra flux and things to compensate ash from blast furnace, coke and other places which is coming. Silicates are replaced by low melting glass here in the sinter, reducing the strength of the sinter, but increasing the reducibility. Superflux sinter, the basicity of this sinter vary between 1 and 3. So, depending upon the amount of addition of the limestone, you can if you add more limestone, certainly you are taking care of the extra silica which is getting liberated in the blast furnace through coke. So, there in that way you are adding extra one here. So, it will take care of the silica which is getting generated in the blast furnace, and that is called superflux sinter, and that will anyway reduce your coke consumption in the blast furnace. So, with basicity 1.6 to no actually 1 to 1.6, it's a little long, it is 1 to 1.6 or CaSiO2 ratio 0.8 to 1.4, sinter strength actually decreases in this due to volume change accompanied by phase transformation from beta to gamma dicalcium silicate, which results in crack formation during cooling. So, this sort of basicity is not desired because due to the formation of gamma dicalcium silicate, and this reduces your strength of the sinter. But if you increase the basicity ratio more than 1.6 or in CaSiO2 1.4 to 2.8 and this is 1.6 to 3, then glass is formed by calcium silicate or calcium ferrite. So, the quantity of this latter increases with increase in the basicity, which enhances the reducibility of the sinter and the formation of various phases shown in this. So, as we were talking at the basicity, it goes beyond 0.8 and 1.6, your strength decreases yield also decreases. You can see that one. So usually that basicity is avoided because tumbler index goes down. These we have talked during the raw material selection. So basicity somewhere here or in the superflux actually, and this is the one where you use it, and this gives a good reducibility to the sinter. And the various phases which are formed, you can see as the basicity increases, your calcium ferrite and hematite formation actually facilitated. Hematite is a higher oxygen stage, while magnetite is a less oxidized stage. So that reduces. So in that way, it is good in the blast furnace. So this sort of superflux sinter are good for reducibility viewpoint or even the strength one, and you can see how these phases are appear in the sintering with the time. Hematite is this one, then you have a, so hematite is going this, you have a ferrite, you have a magnetite. So I think longer you give the duration to sintering, more magnetite is formed, and then you have other phases. In fact, the reducibility of this, you can see the degree of reduction, how it will affect. So reducibility decreases, quite high reducibility. Then hematite calcium ferrite, this is second, lowest one actually is the ferrite, where the reducibility is very low. So this is in the order of decreasing reducibility. So mostly you would like to have these phases in the sinter for the good reducibility, and superflux one that we had seen gives these phases quite good. The sinter quality and test, but I think before that I will, this is also another one which we haven't talked about, the alumina and magnesia effect on the sintering. So excess alumina makes slag more refractory. So this is actually not good. So it reduces the strength and the reducibility if it is more than 2%. However, the magnesium content is more resistant toward the reduction disintegration. So it's good to have this, which is due to formation of spinel structure and thus having a higher liquidation and melting temperature. This also increases your cohesive zone becomes narrower, and which is required, which you want it that cohesive zone should be bit liquidate temperature should become higher. So melting should occur at high temperature, which is a good requirement in the blast furnace, and that helps the magnesium here. And now we will come to the sinter quality and test. So these we already discussed during the iron ore and coke description. So not going to repeat really, but some important one is that reduction under load and softening melting test are important one in the sinter, which are routinely carried out to check its quality. Now there is one problem on this sinter plant which is given here. So the example one, so this says in the sinter plant, the sinter mix is moistened while being pelletized on a flying disc before feeding to the sinter strand. If the mix has 1% water initially and 7% water is desired after pelletizing, how many kg of water are required per metric ton of mix on dry basis. Also find out the water requirement per ton of wet feed and what should be the solution. So, what we are assuming a 1 metric ton of dry mix. So, mix is having a 1% water initially and 7% that is the one which is coming out. Okay. So, we have a this disc pelletizer, the input is 1% H2O water in that mix, and you are adding extra water to get pellets having a 7% water in it. So, if the total weight of water in the output stream, so this we can is a W naught H2O, if that is the total weight. So, normal mass balance of the water will give W naught divided by this, and weight of the water should be 0.07. So, if we solve this, so essentially what we get the amount, so 1000 is coming on because we are doing on metric ton basis. Okay. So, the added amount of the water, not the added amount, the amount in the output pellets in a 1 metric ton of this is about 75.27. So, now in the feed how much we are mixing we can calculate because it gives a 1% is having. So, again in the same way doing the mass balance, if weight of the water in the mix feed stream W prime, then again the same sort of a mass balance will give you 10.1 kg. So, essentially the water which we are adding would be, and this 75 minus this because this 10 kg is being carried over with that. So, that gives you about 65.17 kg per metric ton of solid. Now, in terms of wet feed, we are already we have put 0.1 and saying 1 metric ton. So, essentially 10 kg of water we have supplied in the feed. Feed is carrying over that much. So, again if we do the mass balance and W naught the way we have defined here to weight of the water in the final feed, the mass balance will give you now this 10 kg has to subtract it from 1000. So, essentially dry this ore is 990. So, that should give you this much. So, it is coming about 74.51. Similar way we can then calculate if we subtract the one which is coming with the feed, the actual amount which should be added is about 64.51 kilogram per metric ton of wet mix. And in the previous one it was 65. So, about a 1 kg difference which is coming out. Now, we will come to the pelletization. As I said, this is another name of the granulation we can say. So, it is similar to the granulation as we had discussed in the sintering process. Only difference it uses a particle less than 300 micron size and in which 50% are about 50 microns in size to make the green pellet of 12 to 15 millimeter in size. And the next table actually shows comparison between the sintering and pelletization process. So, if you look at from this table, the feed size in sintering is in this range, while in pellets is in that range. So, this is the major difference between the pelletization and sintering when we are making the granules. mechanism wise does not make much difference except a little. Here as a fuel you use coke grease, here as oil which is high in cost. Product size 10 to 25 and here 12 to 16 millimeter. Product shape of course irregular, here it's regular. Angle of reforge is 30 to 32, 24 to 26. And this is an important thing. Usually you need a low repose angle so that when you are charging in the blast furnace, it could be much flatter the layer, and which is an important thing. So probably we will come about this later. Pipe handling, and this of course irregular, not feasible. Bulk density low, this is quite high, and porosity of course this is high. Voidage is very good in sintering, not that good. Low iron, you have a high iron here. Gang is higher here, but here it is less. High basicity, here is difficult to maintain that. Then you have a problem with the strength and other thing. Good reducibility, here you have a very good one, and that depends on the your basicity, what sort of basicity you put it. So this is sort of the basic difference between sintering and pelletization. In terms of so most of the fines for pelletization comes from iron ore preparation plant, beneficiation plant, blue dust pocket in mines, iron ore fines collected in steel plant, sludge from scrubber, and fines from sizing unit of ore. So as we discussed during our ore section, you do grinding, crushing, so lots of fines are generated. Similarly in sludge, when you are removing the dust from the blast furnace covers, you get that. From the steel plant you collect quite a lot, mill scale and BO, basic oxygen furnace, lots of iron fines are generated. So these all goes to the pelletizing plant. So following steps are there in pelletization. One is the iron ore preparation. So naturally, because many of these feed they do not have the correct size, so you have to do the crushing and grinding and make sure the required size you get it between 100 to 50 micron. And these fines are subjected to washing to remove the gangue material and enhance the iron content in the ore. And so when you do the washing, naturally it has to follow the dewatering, and after which especially in pelletization you put a small amount of binder, mostly is a bentonite, which is a clay based mineral. About 1% or so you mix it, and after mixing you send it to the pelletization plant there for pelletizing unit. So this is an important difference here. And so pelletization of what? So after this, once it goes to the pelletization plant, we have already seen how the disc pelletizer works, how is the what is the mechanism of pelletizing, nucleation, transition, then wall growth, and the size is proportional to the feed rate, and the water which you are putting, the capillary effect, all those come into the picture, and we have already discussed this during the sintering in granulation. So same applies to here, but here the difference is the various pelletization unit we have discussed before. So more or less the same wall formation mechanism applies here. Most popular pelletization units are either disc or drum pelletizer, which were discussed before, and usually you present the result in terms of average size of the pellet, which of course you can define using this formula, where N1 N2 are number of balls and DP1 DP2 are the respective diameter of the ball. So, normal averaging formula by which you can define the average wall pellet diameter. Once you get this pellet form, now you have to harden them because these are the green pellet, does not have much strength. So, it goes to pellet hardening process. In the previous one it was going to the sintering one, in this one it is a pellet hardening. So, individual pellet usually they keep their shape in this case. So, it is not the fusion stage. So, temperature is a little lower in this case. So, as you will see this figure shows the induration machine, and in this one you will see it is quite similar to the sintering machine, but there are many differences. Your main the most popular method to strengthen is thermally treating them, and most popular unit is travelling grade furnace. The important difference is sometimes you are having a updraft. So, the gases are being sucked up from from the starting we put it the green pellet comes are feed from here on the travelling strand, they come over here and they are subject to the drying first here. So, this is actually the updraft thing, gases are being sucked from the top and from the bottom these gases are being supplied, and but these gases are the hot gases of about 350 degrees Celsius, which are coming from the cooling of the pellets, which are at 350 degrees Celsius. From the bottom they are then sucked from the top of the suction unit. So, this gives the drying of the pellet. Then they come to the next section where it is like a preheating of the pellet. So, temperature 350 to 750 degrees Celsius zone, and here you are having a down draft the way we had in the sintering. So, here suction is applied underneath of the moving grate, and these hot air which are coming, these are coming actually after induration, we will come to that section. So, here is a down draft, before is a up. So, there is a difference after passing. So, here the same thing is happening, much more heating and other associated those evaporation and chemically bonded water is going away. Then it comes to the high temperature zone about 1200 degrees Celsius. When it comes to that one, so with fusion of the thing is occurring and you have a updraft here. So, now before that you had a downdraft, now you are having a updraft, and the hot gases actually are coming from the rotary kiln. So, these these hot pellets, they fall they are feed to the kiln where the temperature is quite high, about 1270 degrees Celsius, and from this to this journey the induration of the pellet with fusion of that occurs and the change in the phases occurs, and as I saw in one of the slide previously, that swelling of the pellet occurs. So, all those mineralogical changes may come, and that is why it is necessary to have a proper control of the raw material. So, swelling of this should not occur, otherwise this will create a problem in the blast furnace permeability. So, once it comes through the kiln, the pellet totally are indurated and it comes out, and here the cooling is done, and when you are blowing the cold air, that become hot, and that is the one which is used for the drying purpose. So, here you can see a little complex, you are having a downdraft and updraft of the air, and that is how the induration unit works. Otherwise most and you can see from this figure how the different phenomena are occurring, how much time it takes. So, drying about 10 minutes, preheating another 5 minutes, and mostly then the firing about 10 minutes it takes, and then the cooling. So, these are the sort of steps which similar to the sintering one. So, only the problem you have a combination of down and updraft here. Now, the effect of moisture content that we have seen that time previously. So, we are not going to discuss this, but as we said here finer size, when we are talking more about the pelletized pellet. Coarser size, when we say, this is more relevant to the sintering one. Now, bentonite, when we said as you increase the bentonite, you can see the green crushing strength is increased, which is actually good, but you can't use a very high bentonite because it gives a detrimental effect on pellet swelling and increase the plasticity with added slag. So, up to some extent it is fine. Sometimes even molasses is also used in place of bentonite.